In this video, we're going to be introduced to reactions of aldehydes and ketones, and we're going to focus on one type of addition reaction. And we'll see that carbonyl compounds can react with water. The reaction is reversible, so this is important to understand. And you produce what are called hydrates. Sometimes they're known as geminal diols or gem diols. These types of reactions are analogous to alkene hydration addition reactions. So again, we've seen alkenes react with water in acidic conditions, and you add HOH across the double bond. So here we have a double bond. It happens to be a carbon-oxygen double bond. And so there's going to be parallels between alkene hydration and that of carbonyl hydration. So let's recall the reaction of an alkene. When we take an alkene and we treat it with water in acidic conditions, right, so we have an acid catalyst, we can get addition of water across the double bond. So H and OH adds across the double bond. And of course we had, we looked at regioselectivity of this reaction. But when we take a look at carbonyl chemistry, we see that when a carbonyl reacts with water, again in the presence of an acid catalyst, it can be, or we'll see a base catalyst, then you get the OH always adding to the carbonyl carbon, and then the oxygen gets protonated. So you're still adding water. Notice the parallels. Water is being added across the double bond. There is regiochemistry, where the OH always adds to the carbon and the hydrogen always adds to the oxygen. We're going to see how this works in just a little bit. But this is called a hydrate. Notice on that carbon you now have two OH groups, and this is why it's called a geminal diol, right? Two OH groups on the same carbon, geminal diol. So in this reaction, water is acting as a nucleophile, and it can attack the pi star LUMO of that carbon-oxygen double bond. And if we remember our picture of the molecular orbital diagram of the carbonyl pi system, right? We start out with the atomic 2p orbitals of both carbon and oxygen. We saw oxygen is lower in energy than that of carbon, and so when they mix, we get two new molecular orbitals. One is a pi and of the lower energy, the other is a pi star. When the two electrons come together, they go into the pi bonding molecular orbital. And of course this is the HOMO, right, the highest occupied molecular orbital, and the LUMO is the pi star. So in addition reactions, when water is adding as a nucleophile, the pi system is behaving as an electrophile. It is accepting electrons, and it accepts it into that pi star LUMO of this carbonyl. Now remember that the energy of the LUMO is very close to the energy of the carbon, the original carbon 2p orbital. And so it has a lot of carbon 2p character. And if we represent the molecular orbital, that antibonding orbital, we see that there's a lot of the orbital is expressed on the carbon more than it is on the oxygen. And so when a nucleophile comes in, it's going to attack that carbon. The carbon's electron deficient. So here I have water as my nucleophile. I have a filled orbital with the two electrons on that oxygen, and they start to donate into that antibonding orbital of the carbonyl, which happens to reside namely on the carbon. We can think about this in another way in terms of kind of a resonance, where we see that oxygen is withdrawing electron density away from carbon, so carbon is taking on a partial positive charge. So the nucleophile is going to attack that carbon because it becomes a Lewis acid. The result is, if we're drawing just a curved arrow notation accounting for the electrons, the pair of electrons on the oxygen donates to the carbon, and that carbon-oxygen bond breaks, and the electrons from that pi system go on to the oxygen. Why? Because a carbon can only have 8 electrons around it. So if you're forming a bond, you have to break a bond as well. The result is now oxygen has created a bond with carbon, and the oxygen of the carbonyl is taking on a negative charge. So here I have a situation where I have a plus charge on the oxygen on the left and a minus charge on the oxygen on the right. What happens next is a proton transfer. So we're going to protonate the O minus, and we're going to deprotonate the O H2 plus. And the order of protonation, deprotonation doesn't really matter. Okay, so I'm simply going to show deprotonation and then protonation, but you could do it either way. You could do protonation, deprotonation, or vice versa. So in this particular example, I'm going to take water and I'm going to deprotonate that proton so the oxygen becomes neutral. So now that oxygen is neutral, and of course the carbonyl oxygen still has a negative charge. Notice I form the hydronium ion, and then I can use that hydronium ion to protonate the alkoxide, the O minus. And my result is the geminal diol, right? So this is the way that I form a geminal diol in aqueous conditions. And so if I used, notice in this particular example, all I'm doing is reacting with water. If I protonated first, I would protonate with water, and I would form OH minus, and then I could deprotonate with that OH minus. Either way, I'm forming a geminal diol. Now, we can enhance hydration by adding either an acid or a base catalyst. So let's look at acidic conditions first. When we have water and we add an acid, obviously we get the hydronium ion. So I'm going to use the hydronium ion, and notice it doesn't really matter what acid I use. Typically it's sulfuric acid or phosphoric acid as a catalyst, but it really doesn't matter. What I want you to recognize is the hydronium ion is the acid in aqueous conditions. And it's an electrophile, right? It's electron deficient. And if you remember what we said about the carbonyl, the carbon is a Lewis acid, it can accept electrons, and the oxygen is a Lewis base, it can donate electrons, right? So it is a nucleophile. Recall, when an alkene, if we're looking at the parallels between alkenes and carbonyl compounds, so when an alkene reacts with a hydronium ion, the alkene is the nucleophile, the hydronium ion is the electrophile, the alkene donates a pair of electrons, it undergoes proton transfer, right, and then you form water. So the result is you get a carbocation, hydrogen transfers to one of the carbons, the other carbon becomes a carbocation. Likewise, when you take a carbonyl, the oxygen is the nucleophilic center, right? Remember, the HOMO of that carbonyl bond has more oxygen 2p character than it does carbon 2p character. And so it's that oxygen that's going to accept that proton. Now we can draw it one of two ways. We can draw it as a parallel with alkene, where I'm actually taking the pi bond and grabbing that proton, right? And of course, I still get a carbocation. The hydrogen goes to the oxygen because it again has more of the HOMO has more of the oxygen 2p character. And of course I can draw a resonance structure where a pair of electrons from oxygen donates into that carbon, and I get an oxygen that has a positive charge. So these are two resonance structures of the protonated carbonyl. Now, if I think about this, I could draw this mechanism one of two ways. I've shown where the pi bond of the carbonyl grabs a proton, but I could also show, instead of the pi bond, simply showing one of the pair of electrons on oxygen grabbing a proton. And when I do that, notice what happens. I get this structure. Now notice this structure is identical to one of the resonance structure on the top right, right? And of course I can draw a resonance structure of this. And I see that the result is identical to what I just drew up above. And so typically what we show is we show a pair of electrons from the oxygen. And the reason for this is because if you look at the two resonance structures, the resonance structure that retains the carbon-oxygen double bond and where the oxygen has a positive charge is a major resonance contributor versus the other one where you have a carbocation and the carbon doesn't have 8 electrons around it, so it's not satisfying the octet rule. Notice where you have the carbonyl, the carbon-oxygen double bond, all of the atoms except hydrogen have an octet of electrons. So that's going to be the most stable resonance structure, and therefore we typically will show the lone pair of electrons on oxygen, so the last one that I just showed, grabbing a proton. Okay. Now, there is one other possibility, and I want you to notice this possibility. What if instead of the proton going to the oxygen, what if the proton goes to the carbon? So if I donate those pi electrons to the hydrogen, and so now the hydrogen goes to the carbon and the oxygen takes on a positive charge. Why doesn't this happen? Well, you should be able to see kind of right away that, wait a sec, okay, in one instance I have a positive charge on a carbon, the other instance I have a positive charge on the oxygen. And so you see in this particular case, the positive charge is going on the more electronegative atom, and therefore this does not happen at all. That's where the regioselectivity comes into play. The hydrogen always goes on to the oxygen. Again, think about the molecular orbital diagram and our picture that we've painted of the HOMO of that system, right? That's why the electron or the hydrogen always goes to the oxygen. So overall, we see parallels definitely between the alkene and a carbonyl when we're talking about acid-catalyzed hydration. So if we look at the alkene, what happens in the overall mechanism? The first step is protonation, right? And we form a carbocation. And then that carbocation reacts with water and undergoes an addition reaction. And then in that addition reaction, we get the water adding to the carbon. And now we simply have to deprotonate with another water molecule. So I can show that fairly easily. I'm deprotonating the OH group. We call that step deprotonation step. So protonation, addition, deprotonation, and it leads to the formation of an alcohol. That's what we've seen previously in the first semester when we talked about addition of alkenes. So let's look at the overall parallel of carbonyls. In the first step, what happens? We get protonation. And we form a little variation, right? So the oxygen has a positive charge. Now remember though, there is a resonance structure where the positive charge is on the carbon and you have this carbocation. That's where, so of course we're drawing this resonance structure, right? Because we know the oxygen, this is a more stable resonance structure. but that oxygen is withdrawing electron density from the carbon. So the LUMO of that is still going to reside on the carbon, right? The antibonding, the pi star of carbon is where the water is going to go. So water attacks the carbon and undergoes an addition reaction. And you see the parallels now in that intermediate alkyl oxonium ion step. The last thing that we need to do then is to deprotonate, and we form now not just an alcohol but a diol. Basic conditions are a little bit different. So what are we doing in basic conditions? Well, we're essentially making the nucleophile, which is water, more reactive by introducing hydroxide. Why? Well, if you recall, hydroxide is a better nucleophile, right? Whenever you have a negative charge on the nucleophile, it's going to enhance the nucleophilicity. And so here there is no parallel with alkenes, right? We never saw alkenes reacting with bases. We always saw alkenes reacting with electrophiles. So alkenes do not react with nucleophiles, they do react with electrophiles. And just to show that, why was that if you don't remember? Well, let's think about what happens if hydroxide reacts with an alkene, and the hydroxide is a nucleophile and the alkene is an electrophile. If we think about the addition reaction, the OH attacks one of the carbons, the pi bond breaks, the electrons go to the other carbon. What have I generated here? I have generated a carbanion, and we know carbanions are relatively unstable, and so this isn't going to take place. However, if I look at hydroxide attacking a carbonyl, again, where is it going to attack? Well, it attacks the LUMO of the carbonyl, which has more carbon 2p character. So it's going to attack the carbon-oxygen bond breaks, right, just like I showed up above. And this time, what is the result? Well, now the oxygen has a negative charge. Unlike carbanions, oxygen is much more electronegative and can accept that negative charge. And so we see that the negative charge is on the more electronegative oxygen, and therefore it is perfectly content to accept those electrons. And of course it's going to then react with water, right? We're forming an alkoxide, and we've certainly seen alkoxides before, and the alkoxide then can deprotonate water, and you end up with our geminal diol. Oh, I drew an extra carbon there, so there should not be an extra carbon. It's OH, C, OH, a geminal diol with OH.